Shweta, are we starting now or are we waiting for a little longer?
Sorry, madam, we will wait for 5 minutes. Why? Because the participants will be joining, madam.
Sure, sure. Okay.
Good afternoon, everyone. I welcome everyone to this second day of 1 week online National FDP on fundamental mathematics. The importance of group theory was emphasized very recently when some physicists using group theory predicted the existence of a particle that had never been observed before and describes the properties it should have. Later, experiments proved that this particle really exists and has those properties. Once again, I welcome you for the second day of this National FDP on fundamental mathematics. Now I call upon C. Sunita to introduce today's speaker, Professor Geeta Venkatraman Madam.
Thank you, Shweta. Am I audible, Shweta?
Yes, you are audible.
Thank you. Good afternoon, one and all. This is Sunita, Assistant Professor, Department of Mathematics and Statistics, Raja Bahadur Venkatrama Reddy Women's College. It is my pleasant privilege to introduce today's speaker, Professor Geeta Venkatraman. Geeta Venkatraman is a professor of mathematics at Dr. B.R. Ambedkar University, Delhi. She did an MA and DPhil in mathematics at the University of Oxford. Her area of research is finite group theory. She is a co-author of research monograph titled Enumeration of Finite Groups, published by Cambridge University Press, UK in 2007. Sage Publications India published her second co-authored book titled A Bridge to Mathematics in September 2017. Her third co-authored book, written tentatively entitled Exploring Mathematics Through a Technology, will be published in 2022 by University Press. Madam Geeta was also part of the team that co-authored the policy document Education Technology Roadmap, Technology Vision 2035, Technology Information Forecasting and Assessment Council, New Delhi, Government of India in November 2017. She is currently Dean, Research and Consultancy at Ambedkar University, Delhi. She also served as Dean, Assessment, Evaluation and Student Progression, Dean, School of Undergraduate Studies, and as a chairperson of the Committee for Prevention of Sexual Harassment at Ambedkar University, Delhi. Prior to joining Ambedkar University as a professor in 2010, she taught at St. Stephen's College, University of
Sunita, you got muted.
Sorry. Thank you, madam. She has published several research papers related to group theory, popular articles related to mathematics, and articles on education with an emphasis on undergraduate education. Apart from her interest in group theory and related areas, she is deeply interested in popularizing mathematics, mathematics education, and issues related to women in mathematics, women in leadership in academia. She has given several research talks and popular talks on mathematics in India and other countries to a varied audience ranging from middle and high school children, school teachers, and mathematicians. She has also given talks related to education and also on women in leadership in academia. Professor Geeta has served on several government committees related to both mathematics and education. She has advised several universities in India on their mathematics curriculum. Geeta is one of 5 members of the Committee for the Women in Mathematics, International Mathematical Union Ambassadors from India, and is a member of the Executive Committee of Indian Women Mathematics. She is a founder, member of the Mathematics Teachers Association. She has been on the editorial board of the Resonance Journal of Science Education and is on the editorial board of the Little Mathematical Treasure series of the Ramanujan Mathematical Society. She has also been a member of the executive committee of the Ramanujan Mathematical Society. With this brief introduction, I request you, madam, to deliver the lecture. Thank you.
Thank you so much, Sunita. And thanks, Shweta, and thanks to the college for inviting me to be part of this FDP. And I hope you, I will be talking a little bit about women in mathematics, given that it's a women's college which is organizing FDP, and I'm glad to see a large number of women attending this talk. But also because May 12th, which is Mirza Kami's birthday, has in 2020 it was declared that on May 12th and around May 12th, that is for almost a month around May 12th, the idea is to celebrate women in mathematics. So I will also take a little bit of time to just say a few things about Mariam. You're later on going to have a talk from Nikita on Mariam. I saw that in your FTP schedule, and that's going to be really enjoyable. Nikita is a wonderful speaker as well. So let me get started. And when I come to the mathematics part, I will remind you all about group theory by going over a little bit of its history, and also a reminder of what a group is and some good examples of groups. And only then will I move on to mention some research problems. But the talk is more of an expository nature. I want you to understand why we are interested in this kind of research and give you a kind of overview about it without going into the technical details. And I hope that those of you who become interested in these topics will actually look at the written material that is available, and also anyone who wishes to write to me and seek further references or discuss maths is most welcome to. So let me get started. Okay, why can't I see my desktop? Just give me a minute. Yes. So I hope you can all see my screen.
Yes, madam.
Yeah, thank you. So again, while I'm discussing especially the mathematics, if any of you have any doubts or questions, you can just interrupt and unmute yourself and ask me those questions, because it's better to move with understanding rather than to just sit through a lecture. So as I said, I'm going to sort of have three parts to my talk. The first part, and it's a very small part, which is going to mention something about women in mathematics. And then I will look at the history of group theory a little bit. Then finally, I will move on to groups and to research problems that you can discuss in group theory. Okay. So I've titled this Women in Mathematics, A Long Road Ahead with a question mark because I think we have made a considerable amount of progress, but I do think we also can make a lot more. I've named the mathematicians I put on this in this picture, but I just want to say a few words about each of them. Emmy Noether, she's anybody who does abstract algebra will know about Emmy Noether, and in the she's one of the really well-known women mathematician. But surprisingly, the physicists also own her. They think of her as someone who's contributed seminally to physics. But Emmy was someone who, when she finished school, at that point, in Germany, they did not even admit students, girl students, women students to the university. So you could not go and join, say, a maths, BSc maths or anything in the university. At most, you would be allowed to attend lectures if the professor allowed you to, gave permission for you to sit in the lectures. But thankfully, in a few years, the laws changed. She was actually able to go to university in Erlangen, complete her PhD, and then she moved to Göttingen, which was at that point arguably the center for mathematics in the whole world. It had Hilbert, it had Felix Klein, it had many, many other mathematicians who were well known. And Emmy was part of the group there, but again, the laws did not allow women to hold positions in the university. So she was an unpaid kind of teacher there, but she did such extraordinary work. Abstract algebra and the way in which we study rings, modules owes a lot to Emmy. And in fact, we have objects called Noetherian rings. Okay, so there's a condition on ideal chains, which Emmy is named after Emmy Noether. But I just want to say that she had part Jewish blood, and when the Nazis were in ascendance in Germany, she had to leave Germany. She moved to the United States. She worked in Bryn Mawr College there. She guided PhD students, but died quite young. I think she's supposed to have had cancer of the uterus, but she was extraordinary in the period that she lived. The rest of the people are all thankfully, I mean, Mariam I'll come to later, but the others that I've put down, I'll quickly mention Ingrid Dubashi. She was a woman president, I think the first woman president of the International Maths Union. And all of you, I'm sure, take pictures, and you would have noticed that the digital photographs are saved as JPEG. .jpeg is the extension of the file. Ingrid's mathematical work is responsible for JPEG, and she does extraordinary work which has lovely applications. And I'll just share one other anecdote about her. I heard her give a talk where she said, we should really have a sticker which says mathematics inside, and we should put it on objects which have got developed because of mathematics, or mathematics can be used to study them. And if you start doing that, you'll pretty much realize that all of the things around you could take a sticker, including the human body. So that's how important mathematics is. And now I'm going to come to the three Indian women mathematicians that I've named, I've put down here. Parimala and Sujata are both products of the Tata Institute of Fundamental Research in Mumbai. And I mean, they are people who are known worldwide for their mathematics, have won many prizes. Sujata, in fact, is a recipient of the Shanti Swarup Bhatnagar Prize, and Neena Gupta has most recently won the Shanti Swarup Bhatnagar Prize. She's currently in Indian Statistical Institute, Kolkata, and is doing extraordinarily well in research. And Mariam is someone I mentioned. She's, in fact, the only woman to win a Fields Medal, and I hope you all know about the Fields Medal. We don't have a Nobel Prize in mathematics. What we do have is Fields Medal, and that is much tougher because you have to be below 40 years to get the Fields Medal, and there are at most 4 awarded every 4 years. So Mariam was, the only woman to have won the Fields Medal, and she died soon after winning the medal, in fact. And India hosted the maths, the main ICM, the International Congress of Mathematicians in Hyderabad, in fact, in your city, in 2010. And just before the ICM, we had an event called it was called ICWM, so International Conference of Women Mathematicians, and it was held 2 days prior to the ICM, and it was the first time that they had a women's conference, attached to the ICM in a sense. And Mariam was one of the speakers there, and I had the good fortune to listen to her, and she was extraordinary. Even then, she was predicted to as someone who was in the contention for the Fields Medal. And I think maybe her fight with breast cancer had already begun at that time. She leaves behind, at the time when she died, she had a small daughter, and it's most unfortunate that we lost her very young. But May 12th has been chosen for celebration of women in mathematics. And because it's the birth date of Mariam Mirzakhani, and this was an initiative proposed by the Women's Committee of the Iranian Mathematical Society. Mariam is Iranian, and in the previous ICM, which was held in Rio, there was again a women's meeting. I'll mention that later. It's called WM Square. And that's where this was proposed, and everybody agreed to it. And now we have a May 12th initiative. In fact, I hope you've registered your FDP also as part of the May 12th initiative. Any mathematical event that happens around that time, which encourages women in mathematics, can be listed in that initiative. And it's a worldwide initiative that takes place, as I said, in this period. Nikita, Riddhi and I wrote an article for Resonance on Mariam Mirzakhani, on her life and on the mathematics. And it's written for an informed layperson, which means that it's not technical and that anyone can read it with some reasonable background and get a sense of the wonderful things that Mariam did in her short life. And I just want to mention a few more things. I mean, you would have noticed this yourself, that when you look at women in mathematics in general, at the undergrad level, we're doing quite well. And even in the masters, it's classes in urban cities. And even if you look at the entire data for the country, are very positive. They are very close to 50%. Sometimes it even crosses that. Unfortunately, about 10 years ago, PhD, it was quite bad. Women doing PhD, the numbers were very low. But interestingly enough, now, if you look at the latest data, we have at least 46% of PhD students in mathematics are women. So that's a very, very encouraging sign. And I think what you also see is that at least in urban centers, in urban cities, maths departments at the undergrad level also have a large number of women faculty members. Unfortunately, that doesn't remain the same as you go higher. And also, if you go to institutions which are higher up in the academic ladder in some sense, if they're research institutes or they're institutes like the Indian Statistical Institute, IITs, and so on, then you find that the percentage of women at entry level onwards to higher levels goes down greatly. So there's still a lot of progress to be made. And how can we do this? I mean, it's not just society which is responsible, because I mean, there are, if it was only society, then, in every subject, you should find that the number of women is very low. But that's not the case. We find that particularly in mathematics and certain STEM science subjects like physics, and the more pure you get, the fewer the women that are there, particularly at the top levels. So, one of the things to do is to encourage young people to take up mathematics and to continue with mathematics, to show them that you can have a good career doing mathematics and enjoy yourself as well. Okay, so there are a lot of societies which have been set up to encourage this all across the world. And in India too, we've been doing a lot of things, especially since 2009. Before the ICWM in 2010, we wanted to start having more focus about women in mathematics. And there was a very nice conference organized in Jawaharlal Nehru University in Delhi in 2009. And in the conference, we made sure that at least 50% of the women, over 50% of the women speakers were women, and similarly over 50% of the audience were women. And then we have the Indian Women in Mathematics, and that's something that's been, people have been active. It's been funded by the Government of India, National Board of Higher Mathematics. There are regional conferences, workshops. There are now events for young women students. So I would urge all of you to look at the website, and you can find a lot of information on current activities that we do, and please join in and participate. And I can assure you that the events are great fun, both for men and women. It's open to everybody. We want to encourage everybody to do mathematics, but especially women to do mathematics. And as mentioned, I've had the good fortune to be involved with IWM right from the beginning, and I continue to be involved with them. The other thing I want to mention is that the Association of Women in Mathematics, which is a US-based association, it's the oldest one. It turned 50 years, and they brought out a book titled 50 Years of Women in Mathematics. And again, Nikita, Amber Habib, and I wrote an article, a chapter in that book, which traces the history of Indian women in mathematics. So if any of you are interested in finding out more about what has been happening in India to encourage women in mathematics, please look at that article. And this is a picture here from WM Square in Rio. And seated second from the right is Riddhi Shah. She was the chairperson of Indian Women in Mathematics from 2016 to 2019. And in the picture on top, the second person from the left, Neela Natraj, she's a member of the Committee for Women in Mathematics. She, in fact, chaired the Indian Women in Mathematics from 2019 till 2022. Now we have Vijay Lakshmi from PIFR, who's the chair. And of course, Committee for Women in Mathematics, that's part of the Indian International Maths Union, which does a whole lot of activities to encourage women in mathematics. Also, non-mathematicians are interested in looking at women in mathematics. The EPW, which social scientists will know very well, 3 of us women mathematicians were asked to write about our own lives and how we got into mathematics and so on. So if you want to read more about that, you can see it there. The Department of Science and Technology has lots of wonderful schemes. But one thing that the Indian Academy of Sciences brought out is called Leelavati's Daughters. It has little life stories, 2-page about women scientists. So that's a very, very nice book. It's very encouraging. Sometimes you realize, in fact, Sujata and Riddhi are both people who've written there. You can read about how they got into mathematics. And the only way forward is for all of us, men and women, to ensure that no maths potential is wasted. Okay, so that's the bit that I wanted to say about women in mathematics, also because of the May 12th event. And now I want to take you through a little brief history of group theory. And I'm sure all of you recognize the quadratic roots which are given by this formula here. So the quadratic equation is ax square plus bx plus c equals 0, where a, b, and c we take as real numbers, a is non-zero, right? And in school, you would have learned how to complete squares and get this formula. So can I ask everybody to mute themselves, please? Somebody's unmuted. So this formula, you can see that there are 2 values here. They are the 2 roots of this quadratic equation. So, I mean, you can ask, what is the connection between quadratic equation and group theory? Okay, the point I want to make is that if you look at the roots that are expressed in this quadratic formula, this A, B, and C are nothing but coefficients of this equation. And how have we got the formula? We've done some arithmetic on it. So there's addition, there's subtraction, there's multiplication, division, and extraction of roots. Okay. So if you can write down the roots of an equation by doing arithmetic on the coefficients, which is addition, subtraction, multiplication, division, and extraction of roots, then we say that we can solve this equation by radicals. That's the definition of solving an equation by radicals. So the quadratic formula has been known for thousands of years. And then obviously, you know, when mathematics started developing, people wanted to know, can you solve the cubic equation also by radicals? That is, if you have an equation which is ax cubed plus bx square plus cx plus d equals 0, you want to know whether you can write down the 3 possible roots in terms of the coefficients and arithmetic on the coefficients and extraction of cube roots now. So the question really was, can you solve a cubic equation by radicals? And the story of that is very interesting. The general cubic equation came up in the 16th century, and the algebraists involved were Scipione del Ferro, Tartaglia, and Cardano. Okay, so again, I would like people to mute themselves. The first, so cubic, you have to remember that people in those days were very uncomfortable with negative numbers even. So, okay, whoever is unmuted, please mute yourself. It's disturbing everyone, including me. So the first person so you know, what they did was they classified the cubic equation in 3 different types because they didn't want to deal with negative numbers. So one type of equation was solved by this person called Scipione del Ferro. And he never published his work, but he shared the solution with a few people. And one of them was his student called Fiore, who otherwise was not a great mathematician. And then in those days, so this is the 16th century in Italy, if you knew a piece of mathematics and you knew to do it well, it brought you a lot of fame. You could, you could, like you in Hindi movies, you will challenge somebody to a fight over something. In those days, you could challenge somebody to a mathematical fight. So Fiore Tartaglia was somebody who was at that. Tartaglia actually means the stutterer. His actual name is different, but he was, known to be a good mathematician. So this Fiore in 1535 challenges Tartaglia to a mathematical duel. So what happens in the mathematical duel? Fiore gave 30 questions to Tartaglia to solve, and Tartaglia similarly gave 30 questions which Fiore had to solve. And the loser had to pay for 30 banquet dinners. Okay, so that was a lot of money to lose if you actually lost. Now, Fiore's questions were all based on solving the cubic equation of a single type, which nobody else knew the answer to except Scipione del Ferro and Fiore, because this was completely secret. But Tartaglia worked really hard, and not only was he able to solve cubic equations of that first type, but he was also able to solve all cubic equations. And the methods discovered actually tell you that a cubic equation is solvable using radicals. That is, you can write down a formula for the 3 roots using just arithmetic on the coefficients and extraction of cube roots. Now, once Tartaglia won the challenge, he shared the solution with someone called Cardano, who was actually an Italian doctor. And but he was sworn to not reveal the solutions. And then Cardano actually managed to use the method for the cubic equation to solve the 4th degree equation along with Ferrari. And the problem then was they wanted to publish their work, but they had to use Tartaglia's work to do it. This is what happens in mathematics. Every time we do a new bit of mathematics, it's based on what went on previously. So they wanted to publish their work, but they could not do so because they had promised that they would not reveal Tartaglia's solution. Anyway, and he was adamant that no, you cannot reveal. So the end result was that Cardano discovers that actually Scipione del Ferro was the first one to solve one type of cubic equation, and then he uses that fact to publish the solution. Tartaglia is very upset. He also puts out another challenge later on and he loses. But so there's a lot of story, mystery, intrigue about how the fact that cubic equations and 4th degree equations could be solved by radicals. So as mathematicians, what would the next thing strike? The next thing that would strike you is what happens to 5th degree equations? Can we again solve them using radicals? And the thing is that the answer to that is actually no. But before that, I want to mention that Lagrange also looked at equations of degree 4, and you would have heard of Lagrange's name if you've been studying mathematics. But the first person who showed that the 5th degree equation was not solvable by radicals was Abel. So those of you who've done group theory will know about abelian groups, and abelian groups are based on, are named after Abel. And it was, a very seminal work, and it was published in Krell's journal, and that's the oldest maths journal that we have, and it was published in the first volume of that. So, okay, so up to 4 you can solve by radicals. 5th degree you cannot solve by radicals. So what next? And then we come to Galois. And the problem was that the methods that Abel used would work only for fifth degree equations. It was not something that you could use for higher degrees. And Galois comes, he's so young, he was just 19 years old, and he's thinking and doing mathematics which is far ahead of his time. So almost nobody understands what he's doing. Okay, so that's another problem that happens when you're a genius and you're young and you're discovering new things which nobody has done before, at least not in the way that you are thinking about it. And in fact, in Galois' case, he actually literally invented new things to try and solve this problem. So what he did, and this is a method that we use in mathematics a lot. So on the one hand, there is a problem which is to do with finding roots of equations, right? And you want to know if sixth degree equations and higher degree equations can be solved by radicals. But it's very difficult to solve it just by looking at those equations and the coefficients and so on. So instead, what Galois does, to each such equation, he associates a group. It's a group. So he invents groups, and to every equation you can associate a group. I will loosely call it the Galois group of that equation. And he proves a result which kind of says that you can solve this equation of nth degree by radicals if and only if its Galois group satisfies a very important property which he calls solvability. Solvability just means that you can kind of break up that group into smaller sections which are very, very nice. I'll just leave it at that. I'm not going to go into detail about solvable groups right now, but that's what he does. So he's taken the problem about roots of equations, moved it to a completely different realm, which is group theory, and he shows that these two are equivalent. That is, the equation being solvable by radicals is exactly the same as the Galois group being solvable. And then group theory tells you that if you look at the general equation of degree 5 and above, the Galois groups associated with those polynomials are not solvable groups. So immediately you get that for degree 5 and above, equations cannot be solved by radicals. That is, you might be able to solve one particular equation or the other by writing down the roots. But in general, if you are taking an arbitrary nth degree equation, ax to the power n plus bx to the power n minus 1 plus dot 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 up to the constant term equal to 0, then you cannot write down the n solutions in general using arithmetic on the coefficients and extraction of roots. It's not possible. Okay, so that's what he showed. And he dies very young. He's just 21, and his work is published after his death and actually leads to an area of mathematics which you study usually at the post-graduation called Galois theory. And so he was the key person to talk about this group of permutations on the roots of an equation, which led to the Galois group. And of course, I mean, there were various others who contributed: Poisson, Liouville, Jordan, Cali. So Cali's theorem is something that you study in group theory again. Walter von Dyck, Burnside. Burnside, in fact, in 1897 publishes a book which is called Theory of Groups of Finite Order. But in all of these people still didn't think of groups in a very abstract way. They thought of them more as functions or operators on some set of objects. And strangely enough, after having developed abstract group theory, we used representation theory to actually start thinking about abstract groups as, groups of functions or groups of matrices and so on, so that we are able to make headway within them. But in general, even as late as 1897, we did not have the abstract definition of a group that we use nowadays. So it actually comes up only that the 20th century definition is something that basically comes up by, around this period. Just after 1897, early 1900s is when you get that. And so let's remind ourselves of how we define a group. So a non-empty set G with a binary operation. So it's a good way of combining things in your group. Because it's a binary operation, that means if I take two elements from G and operate with using star, I go back to G. So it's already, there's closure there already. So you have closure under star, you have what is called associativity, and then you have the existence of an identity element, which basically says that there's this unique element E, such that if you operate with E on either side, you stay where you are, right? So A star E is A equals E star A, and for each element there is again a unique element called its inverse. So if you have a non-empty set with a binary operation, so it's already closed, and if it's associative, there is an existence of identity, and with respect to that identity, every element has inverses, then you call such a non-empty set a group along with that operation star. So the group is not just the set, there is the operation also which comes with it. Along with it, if you have that A and B commute with each other, that is A star B is B star A, for every A and B in G, then we say that the group is abelian, right? And as I said, identity and uniqueness of inverses are there. Identity is also unique. There are various little results that you can prove about inverses and so on. So what are the major examples of groups? So you have our number systems, Z, Q, R, C, they're all infinite abelian groups under addition. If you look at at rational numbers, real numbers, and complex numbers, the non-zero versions, they are infinite abelian groups under multiplication. And if you take entries from either integers or rationals or reals or complex and look at the n cross n matrices with entries from them. In fact, if you take m cross n matrices with entries from them, then under addition, it forms an infinite abelian group. And in all other cases, if you look at the invertible n cross n matrices with entries either from rational numbers or real numbers or complex numbers, then it forms a group under multiplication. So it's what are the invertible matrices? They are the square matrices whose determinant is non-zero. So the general linear group forms a very important group of study. In fact, I'll be, a lot of the work in group theory research work involves what is done using representation theory, where you try to move your group from its abstract setting somehow into the general linear group and to be able to study it there. Okay, and another matrix group which I use a lot is where you have what is called the finite field. So you can I'm sure you people have studied this, but if not, I'll give you an example a little later, just in the next slide. But finite fields are fields with finitely many elements, and it turns out that it has to be a prime power, the number of elements. And then the general linear group becomes a finite non-abelian group in general, with particularly if n is greater than or equal to 2, and its order is given down there. Okay, and the cyclic group of integers under addition modulo n, that's a very standard example. The group of co-prime integers to n, which forms a group under multiplication modulo n. These are both very, very useful examples of finite groups. And most importantly, the group of permutations. So these were the kinds of groups that Galois himself dealt with. So if you start out with a set X, which is non-empty, and you look at all the bijective functions of X, we'll call it Sx, that forms a group under composition of functions. And if the set X itself has 3 or more elements, then this group has to be non-abelian. If X has exactly n elements, then we take X to be the set 1, 2, 3 up to n, and instead of Sx, we write Sn. If X has infinitely many elements, then Sx turns out to be an infinite non-abelian group. This is a very useful example of group. And Cali's theorem in group theory tells you that every group is basically a permutation group. You can think of it as a group of permutations. Another very important group is called the group of symmetries. So if you can do it in, you can define it in general for a subspace of a metric space, but I will stick to the coordinate space Rm. So if you take any subset of Rm, there's a concept of distance between 2 points in the coordinate space Rm, or the vector space as you call it, Rm. And it's given by the Euclidean distance formula, right? If you have 2 points, one of them is x1, x2, x3 up to xm, and the other is the point with coordinates y1, y2, y3 up to ym, then you know that the distance between these 2 points is given by square root of xi minus the sum of xi minus yi squares, right? So that's the distance. And what you can do is you can look for the functions which are, so you take any subset X of Rm, and for, so look at the functions which are bijective on X, but also preserve the distance between any 2 points in X. So these are called the symmetries of X, and they are of particular interest when X is a geometrically defined subset. So for example, the easiest thing is to look at the plane, which is R square, and we could be looking at, regular n-gons. So the equilateral triangle, the square, the regular pentagon, and so on. And when you look at the symmetries of these things, they form a group, and for the regular n-gon, the group is called the dihedral group of degree n. It has 2n elements, and for n greater than or equal to 3, it turns out to be non-abelian. And it turns out that the elements of Dn are nothing but rotations and reflections, and it has exactly n rotations and n reflections. If you look at a square, for example, you can have rotations about the center of the square of 90, 0 degree, of course, nothing happens. Then 90 degrees, 180 degrees, and 270 degrees. And similarly, you can reflect about the, the vertical line dividing, cutting the square into 2 vertical halves, which if you can superimpose on each other and they'll match up. Similarly, there's the horizontal line and the diagonal lines. So those 4 lines, you can reflect about them. And this you can generalize. For a rectangle, there are 2 rotations and 2 reflections, and it turns out to be an abelian group, and it's called the Klein's 4 group. Okay? So in general, when you look at Dn, you can think of rho as a rotation by angle of 2 pi by n. So in a square, n will be 4 and 2 pi by 4 will be 90 degree. So rho can be thought of as a basic 90 degree rotation for a square. And what are the rotations then? There is the 0 degree rotation. Then there is rho, which is the 90 degree rotation. Rho square will be 180 degree rotation, and rho cubed is 270 degree rotation. If you apply rho 4 times, you get back to the identity, which is the 0 degree rotation. And sigma you can think of as any reflection. It's of order 2. Reflection have I mean, if you apply a reflection twice, you get to the identity, right? So, and you can actually have a nice way of representing all the elements of Dn. And you can also have planar figures which have no reflections, but just rotations and such things also. They have the cyclic group of order n as their symmetry groups. In fact, if you look at finite planar figures and you know they have finitely many symmetries only, so they're not like the circle, then it turns out that their group of symmetries either has to have equal number of rotations and reflections, so it will be a Dn, or it will have only rotations, so it will be a Cn type. And this is a fairly complicated theorem to prove in group theory, but it's a very nice theorem which controls the way in which, which tells you what types of symmetries are really possible in real life, in a sense. So now I've given you a basic background with groups, and we've already seen that, groups, they on the surface can appear very different, but in reality, they are one and the same. So for example, if I look at the symmetries of a rectangle, I said that there are 2 rotations and 2 reflections there. And at the same time, if you look at U8, which is the set of integers which are co-prime to 8, positive integers. So that's 1, 3, 5, and 7. Again, 4 elements there. And what is the operation there? There it is multiplication modulo 8. And you will actually see that U8 and the symmetries of a rectangle are actually the same. It's just a group, one group in a disguise. Okay, so once you know this, formally we say that these 2 groups are isomorphic. Okay, so isomorphism between groups is basically a bijective function between the 2 sets, which also preserves the group operation on both ends. So the question that you can ask is that, suppose I'm given an order, say 3. How many groups do I have up to isomorphism of order 3? Yeah, and that is fairly easy to answer. When you start with group theory at the undergrad level, you can very quickly, just by very basic things, prove that actually any group of order 3 just looks like there's an identity element, there's an element A, and then there is an element A inverse. Okay, and A square and A inverse are one and the same. And when you look at A cube, you come to identity. So every group of order 3 looks just like that. So up to isomorphism, there's only one group of order 3. When you come to 4, so 2 also, there's only one group of order 2. There's only one group of order 1. When you come to a group of order 4, you can have, like, take the 90-degree rotation of a square. It has, if you apply it 4 times, you get identity. So if you look at 1 row, row square, row cube, that's a cyclic group of order 4. And that's very different from the symmetries of a rectangle, which we call the Klein's 4 group, which is also a group of order 4. It turns out these 2 are not isomorphic. So when you look at a group of order 4, you have 2 distinct groups up to isomorphism of order 4. So in general, this is a question that you can ask, and this is a research question now. How many groups of order n are there up to isomorphism? So in the area of enumeration of finite groups, the aim is to find the answer to this question and other related questions. So what we do is we define this function f of n, which is defined as the number of groups of order n up to isomorphism. And here's a table. I'll give you 2 seconds to look at the table. It tells you for the different n's, how many groups are there up to isomorphism of order n. So you'll see in the table, some of the cells are highlighted in purple. Those were the n are prime there, 2, 3, 5, 7, 11, and 13. And basic group theory tells you that any group of order prime order has to be cyclic. So there's only one group of prime order. So that's why f of n in these cases is 1. Then 4 and 9 have been colored similarly because they are of the type p square, prime square, right? 4 is 2 square and 9 is 3 square. Again, basic group theory tells you that a group of order p square has to be abelian, and you can have two types of groups of order p square, either cyclic of order p square or what is called the direct product Cp cross Cp, the direct product of two cyclic groups of order p. So that takes care of 4 and 9. Then you have, I've highlighted 6, 10, and 14. They're of the type 2p, where p is prime. And in this case, we find that there are exactly two groups of order 2p, where p is prime and odd. And one is cyclic, and the other is the dihedral group for a regular p-gon. Okay, so those are the only ones that you have. What about the rest? So there's 8, which has 5. There are 5 groups up to isomorphism of order 8. There are 5 groups up to isomorphism of order 12. There's only one group of order 15. And when you come to 16, which is 2 power 4, there are suddenly 14 groups. 15, it's not too difficult to show that there is only one. But 8 and 12 already become slightly difficult. You tend to do them towards the end of a undergrad group theory course or the beginning of a master's level course. That there are 14 groups of order 16, I'm not even sure, I mean, is quite tough to show. And in fact, these 2 powers create a lot of problem. And so let me give you this interesting fact that it is known that, so 2 to the power 10, so 2 to the power 4 is, 2 to the power 5 is 32. So this is 2 to the power 32 into 2 to the power 32. So it's 2 to the power 64. I mean, sorry, what am I saying? 2 to the power 5 is 32. It's 2 to the power 5 into 2 to the power 5, which we are looking at. So that is 32 into 32. And the number of groups of that order up to isomorphism is 4, 9, 4, 8, 7, 3, 6, 5, 4, 2, 2. That's a very large number. But we don't even know even now how many groups are there up to of order 2 to the power 11. But it is known that there are at least 2 to the power 44 such groups. So you can see 2 to the power 44 is a very huge number. Okay, so in general, it's very difficult to find out what Fn is. So instead, what you want to know is that as n grows large, can I identify a nicer function of n which I understand, which is very close to f of n. Okay, so that's how we proceed. So we want to know approximation to Fn as n grows very large, right? So, and we can also generalize this by saying that let S be a class of groups and let Fs of n be the number of isomorphism classes of groups in S of order n. So S could be abelian groups, it could be solvable groups, varieties of groups, P groups, and so on. And you know, depending on what characteristic S has, that tells you the structure of groups inside it, and you use the structure of groups and representation theory and combinatorics, sometimes number theory, sometimes analysis to try and find out something about the behavior of this function Fsn as n grows large. And particularly in finite groups, since we're dealing with them, the Sylow subgroups play a very important role. And in abelian groups, of course, the entire group is abelian. But there's an intermediate category of groups called A groups. They are groups which may themselves be non-abelian, but their Sylow subgroups are abelian. And then finally, you can look at groups in general, and it turns out that the enumeration function behaves, jumps substantially as you move from one level to the other, from the abelian groups to the A groups, and from A groups to groups in general. And these are some of the results that have been proved. And a very, very important result was proved in 1991 that the number of groups of order n is less than or equal to n to the power constant times mu n square, where if you have the prime decomposition of n, mu n is nothing but the maximum of the alpha i's. And this proved a long-standing conjecture and was published in the Annals of Maths, which is one of the topmost journals in mathematics. And it was by a Hungarian mathematician called Lotzi Pieber. And the work on group enumerations began largely in the 1960s. There were various results about P groups that came up there. And then, of course, people worked on things. They came up with conjectures, which, as I said, was proved in 1991. It was published in 1993. And so this is, the bound, upper bound that you have for f of n. So basically what it's saying is, when you look at f of n, the number of groups is like n to the power 2 by 27 mu n square, where mu n is the maximum of the alpha i's, where the prime decomposition of n is p1 to the alpha 1 up to pk to the alpha k and so on. Okay, so I'll skip over this, but a lot of questions are still open in this area of group enumerations. So when you look at solvable A groups, we still don't know the best upper bounds. We don't know another very interesting question about groups, which is that is the enumeration function onto? That is, if I give you a number, say 1001, is there an n such that f of n is exactly 1001? Okay, so that's the kind of question I want to answer. And there's a lot known about it, but it's still open. Okay, and I'll just finish. So this is the area of group enumerations, and I'll give you a reference. The book that we wrote has all you need to know about group enumerations, and also gives you a lot of open questions to work in. But group theory, now there are a lot of interesting research problems, which at least to state are quite easy and quite interesting. And one area which has developed greatly again in the last several decades is an area called group theory and graph theory. So you can associate graphs to groups in different ways, and then you want to study about the group, properties of the group via the graph, and maybe the properties of the group by knowing, properties of the graph by knowing the group. Now, one of the oldest graphs that you could associate with a group was called Cali graph. And basically what it says is, so you can start out with a group G and take any subset S of the group. Okay. And the only condition is that the identity element should not be there in S. And then the graph has as vertices, each group element is a vertex in the graph, and you draw an edge between the two group elements G and H if GH inverse belongs to the set S. Okay, so the Cali graph, of course, it depends on the set S, right? For the same group, if you change the set S, the Cali graph will look different. And I've taken these pictures from, I'll show you the reference later. So this is the Cali graph for integers, where the set S is just taken as the set with 1, right? So 0 plus 1 will give you 1, 1 plus 1 will give you 2, 2 plus 1 will give you 3, and so on. So you can have edges that way. And similarly, from if you add 1 to minus 1, you can get to 0. So you'll have edges like this. Okay. On the other hand, if you take the generating set to be 2 and 3, the graph looks like this. So from 0 can get connected to 3 because 0 plus 3 gives you 3. 0 can get connected to 2 because 0 plus 2 gives you 2. And so you get this kind of a picture for the same group Z. Right? So there is something called the Cali graph, and people study Cali graphs, and you can put the distance on Cali graphs, and there's a whole lot of work, which is research work, which is done on that. But there is a lot of other graphs that you can associate with a finite group. For example, so you can look at the primes which divide the order of a finite group, and you can have a vertex for each prime. And then you join any two primes together only if there's an element of order. So if it's a prime P and a prime Q, you join it if there is an element of order PQ in your group. Okay, and such a graph is called a prime graph. Then there is something called commuting graph, where again the vertices are elements of G, and G and H are joined if GH is HG.
sound.
Yeah, so basically what happens is that you can, as I said, you can find out when will the graph, what conditions on the group will make the graph to be connected. So you can study graph theoretic properties by putting conditions on your group. Or on the other hand, you can ask, okay, this is the kind of graph that I have, what are all the groups which can have this graph as a prime graph? So then using the properties of the graph, you try and classify your group. So there's a huge amount of work that is happening in group theory and graph theory. And there's a reference again, which I'll show, which you can read about this. And another area which I don't have time to go into is cryptography. So group theory and cryptography is also a big area of work now. There are public key encryption is something that you can do using good, big non-abelian groups. So I won't say very much more than that, but these are all areas of research and very interesting research problems that come out of knowing group theory and associated things with it. So these are the references. So if you want to know more about groups and symmetry, it's a very nice book to read by Armstrong. The Enumeration of Finite Groups, which is actually till 2007, all the major results in that area have been discussed, and there are a lot of open questions there. And then I would recommend Peter Cameron's paper, Graphs Defined on Groups. It's a survey paper, and it gives you a very, very good background on graph theory and group theory. These are some of the history website is particularly good for history of mathematics. It's a St. Andrews University website, and I would recommend it very, very strongly to all of you to look at. It also not only talks about mathematicians and their work, it also gives you a history of the mathematical concepts themselves. And the Cali graphs I took from Wolfram Math World. Wolfram is the company which does Mathematica, which has produced Mathematica. They have a lot of freeware to use. It was mentioned that we are working in our new book using technology to explore mathematics is going to come out. And one of the things there, so the cryptography part in that particular chapter, we use Mathematica to explore cryptography. And there's on cloud, you can use a free version of Mathematica. And then the Cali graph for integers has been taken from that website there. And with this, I will stop my lecture, and please feel free to ask any questions.
Ma'am, do you have any proofs for a cubic degree and a fourth degree equation with respect to radicals?
So, I mean, these are very well known. They're standard proofs, but unfortunately, these are not taught at the undergrad level somehow, you know. But there are books in which you can find them. So, in fact, any book which talks about Galois theory, but from a historical point of view, will definitely tell you how to solve this cubic equation. I too have the proof written somewhere. If you send me an email, I will share it with you. And you can reduce the quartic equation to the cubic case and then do it.
Okay, thank you.
You're welcome.
Any more doubts for the participants?
Okay, there's a talk tomorrow on graphs and algebraic structures. So you'll learn more about that tomorrow.
Thank you, madam, for readily accepting our invitation in spite of your busy schedule, and also for enlightening us by your lecture, madam. Madam, this is a small appreciation certificate for you.
Thank you so much.
Accept it, madam.
Yes.
Welcome, madam.
My pleasure. I'm so glad I was able to participate in this. And I wish you all several days more of fun learning new mathematics and enjoying yourselves. So thank you very much. I will take leave now. I think you have another talk scheduled at this point. So
yes,
thank you so much, Shweta.
Thank you, madam. Just, I now call upon Sunita to propose a vote of thanks.
Thank you, Shweta. It is my pleasant privilege to propose vote of thanks on behalf of Department of Mathematics and Statistics of this esteemed institution. At the outset, I thank Professor Geeta Venkatraman, today's resource person, for accepting our invitation and delivering such a wonderful lecture, especially women in mathematics, current scenarios, and history of group theory, and some interesting facts, results, and research problems. Ma'am, we are highly impressed by the simplicity of your lecture. I profusely thank you, ma'am. I would also thank management, especially Professor Sudarshan Reddy sir, secretary cum correspondent of our college, for permitting us to conduct 1 week national level faculty development program. I sincerely thank our beloved principal, Dr. Achyuta Devi ma'am, for her support and guidance in arranging the program. I extend my sincere thanks to coordinator and head Department of Mathematics and Statistics, Shweta Srivastava, for coming up with an idea to conduct 1 week national level FDP. I also thank all the participants from different states across India for their sincere participation. Last but not the least, I thank our faculty members for their efforts in making the program a success. Thank you.
Thank you. Thank you so much, Sunita, and good wishes to all of you.
Thank you, madam.
I will say bye now. Bye-bye.
Thank you, madam.
Thank you, madam. Thank you. Thank you, madam.
Thank you, Sunita.
Yeah, you are welcome, sir.
A quote by John L. Casti. What distinguishes a mathematical model from, say, a poem, a song, a portrait, or any other kind of model is that the mathematical model
Shweta, you are not audible.
Sorry. I just quote by John L. Casti. What distinguishes
Madam, again you are muted.
sorry. What distinguishes a mathematical model from, say, a poem, a song, a portrait, or any other kind of model is that the mathematical model is an image or picture of reality painted with logical symbols instead of with words, sounds, or watercolors. With this, I just welcome Professor T. Suman Kumar sir to the session. For that, I just call upon D. Harita to introduce sir.
Thank you, madam. Ma'am, am I audible clearly?
Yes, you are audible.
Good afternoon to one and all. Welcome you all to session 2 of this day 2 of 1 week National Level Faculty Development Program organized by Department of Mathematics and Statistics at Vidyara Women's College. I, D. Harita, Assistant Professor, Department of Mathematics and Statistics at Vidyara Women's College. It's a great pleasure for me to introduce our speaker of this session, Dr. T. Suman Kumar, Associate Professor, School of Mathematics and Statistics, University of Hyderabad. Sir completed his PhD from University of Paris, and is a research scholar in Tata Institute of Fundamental Research, Bengaluru. Sir completed his Masters in Applied Mathematics from University of Hyderabad. Sir research areas include population dynamics, mathematical biology, numerics of partial differential equations. Under his guidance, 1 student pursued PhD and 5 students completed his master's project. Sir has a teaching experience of more than 13 years in the areas of mathematics include numerical methods and computing, advanced partial differential equations, ordinary differential equations, measure and integration, mathematical methods, discrete dynamical systems, classical mechanics, to name few. Sir has also revealed knowledge on computer skills, on mathematical packages, computer languages, and operating systems. Sir has published nearly 21 research papers in various national and international journals. Sir has also authored 2 books on first course in ordinary differential equations, CRC plus Taylor and Francis Group, Florida, USA, and solutions to exercises of the first course in ordinary differential equations, CRC plus Taylor and Francis Group, Florida, USA. To his credit, Sir has received a grant of rupees 6 lakhs from Sir BSP for his project on time-elapsed neuron model with diffusion, mathematical research in fact-centric support. And Sir has also been received a grant of rupees 1,80,000 from NBHM to attend ICI AM 2015 Beijing. Sir has also been awarded a grant of rupees 1,80,000 from National Board of Higher Mathematics to attend International Congress of Mathematics in the year 2014 at Seoul. For his contributions in the field of mathematics, Sir has awarded Young Scientist Award in Mathematical and Physical Sciences in the year 2017 by Telangana Academy of Sciences, Telangana. Sir has received the gold medal for securing the highest percentage in MSc Applied Mathematics during the year 2003-5 from University of Hyderabad. Sir has been awarded a Junior Research Fellow by CSIR, Council of Scientific and Industrial Research, in the year 2005. Sir has also received fellowship for 2 successive years, that is during 2003, 4 and 4-5 by National Board for Higher Mathematics. Sir is also a member, National Board of Higher Mathematics, Southern Region Library Committee. Sir has been associated with University of Hyderabad from 2009 to till date. He has been contributed to the School of Mathematics and Statistics as a coordinator for MSc and PhD students, a mentor, and he has also organized many conferences, workshops, to name few. Apart from his work, Sir has also interested and associated with other organizations. He has been appointed as Joint Coordinator of Regional Mathematical Olympiad, Telangana region, and he's also trained RMU qualified students for in the Indian National Mathematical Olympiad. And he's also been an examination center coordinator for NBHM for MSc and PhD fellowship test. He also delivered several lectures in local schools and colleges to promote mathematics. Also, sir, to share his deep knowledge in the field of mathematics, sir has given various talks in several seminars and invited as a resource person in workshop. Sir, it is an honor and privilege for us to have you with us today, sir, to listen to your lecture. I welcome you again, sir, and request you to take over the session.
Am I audible? Hello?
Yes, sir, you are audible, sir.
Oh, wonderful. Yeah. First of all, let me thank you for the invitation to be part of your wonderful program, your week-long program. And I'd like to thank the faculty who introduced me. It's overwhelmed by her introduction. Okay, so kind of her. Yeah. Now I would like to. Yeah, I started at nearly 4:30, so I'll try to give lecture for 50 minutes or 55 minutes, and I'll be very happy to answer your questions, whatever. Yeah. And in fact, it is a very difficult task to give a lecture for a group which consists of BSc students and MSc students and faculty. Okay, it's a very heterogeneous group. And let us see whether I can do some justice or not. Okay. Yeah. Yeah. At any point of time, if you think I'm going too slow or I'm going too fast, you are not able to follow it, then feel free to stop me and ask me questions. Okay. Yeah, because this is I think it's a good idea to have maximum possible interaction. Had it been offline, it would have been wonderful. It would be easy to interact with me. But anyhow, let us try to be as what is it, as interactive as possible. Okay. Yeah. Fine. In fact, this Zoom is, in fact, it always troubles me. Let me see whether I can do a lecture without technical glitches. Yeah. Fine. Are you able to see the screen?
Yes, sir.
Okay, fine.
Yes, sir, we can see your screen, sir.
Okay, fine. Yeah. So the topic that I have selected for the for today's lecture is some kind of historical one. As I said, it's very difficult to choose a topic which contains deep mathematics, which can cater to BSc as well as MSc students. So that's why I thought, okay, I will tell stories about how differential equations enter population dynamics, and what are the differential equations that people are working about, and why population dynamics are important, and when did it all start. Okay, let me discuss this thing. Okay? Yeah. So far, let me tell you that since we time of maybe later part of Stone Age, human beings started counting themselves, and they started counting the heads, the animals that they are supposed to they hunt, okay, for various purposes. Okay. The moment they know how to count, the first thing that they counted was themselves. How many of them are there, and how many animals are there of various types. Of course. And then, of course, and in fact, this is just a belief for various reasons. Actual scientific evidence of counting of, populations, it all started, one of the earliest documentary evidence is something like 3800 BC. Okay. So in Babylonia, of course, at the time there were very few civilizations. Okay, Babylonian and Egyptian, and of course Indian. Some people believe that we have this oldest civilization. 3800 BC is in Babylonians. There are documented Babylonian civilization. There are documented evidences of counting of human population. Okay. So therefore, the first historical document can be traced back to Babylonian civilizations. Okay, this is nearly 4,000, no, nearly I think 5,800 years. Okay, yeah. After that, this I would say the next substantial evidence can be traced back to something like 225 AD. Okay, this is this is the time of Roman Empire. Yeah, this is when the first table of mortality, okay, of life expectancy, this was actually made by this was made by various people who do tax collection and so on. Because this Roman emperor, this Mercer, you would have studied in your history books about him. This Mercer asked them to do it. So in fact, while they were counting this Roman Empire and people who were slightly before them, they were doing it's because they wanted to have two types of records. One is land records for the purpose of tax, okay, because they wanted to know who has to pay how much tax. Okay, that is one. And second is for many empires, okay, many kingdoms, people of certain age should be in military. That is compulsory military service. So when they have to plan how many of them are going to join in military service after 5 years, okay, what are the resources that we should have, what are the wars that we should plan, for such kind of reasons, they used to count, how many people are there of various ages and so on. So it's mostly for selfish purposes. Whenever these kings or emperors order something, it's not for the sake of benefit of people. It's for their selfishness. Yeah. Anyhow, whatever be the reason, around 225, the first table of mortality or life expectancy was prepared. Okay. But since it is mostly for the purpose of levying taxes, okay, it was highly inaccurate because whoever paid some bribe to the local guy, that revenue inspector kind of thing, so they got they got away with wrong records and because at that time this corruption was very rampant, I would say. Anyhow, so later on, when the emperor found out that these records are highly inaccurate, these land records and then population records are inaccurate, so he ordered another guy called Ulpian, and in fact, it was done so good, this Ulpian, and this after Roman Empire fell down, these Italians used this nearly for 16 centuries. Okay, these kind of land records and this life expectancy and the rate of mortality and so on. Okay, so after that, the major breakthrough, it came in 1086 AD. Okay, in England. So this is the first complete record of people and land. Okay. In fact, those who are interested in history of England, they would they could not miss this William the Conqueror. Okay, and it is during his tenure, this first complete record of people and land was compiled, and in fact this is called Doomsday Book. Okay, it's Doomsday Book. Okay, so all these things are just, so far there is no modeling, it is just data collection. Okay, data collection. See, data collection is quite a non-trivial thing in those days. Okay, because there was no communication system, efficient communication system. There was nothing much, no computational thing. It is very difficult to add everything. They have to do manually. There were no calculators, nothing. In fact, this how to handle this kind of data, it's a non-trivial question in those days, but they could do it. It's a non-trivial thing. And in fact, in this context, I wanted to make a remark. In India, we don't have that type of culture. Okay, so maintaining records of birth of various people, means birth of a kid, noting this. Noting down the day of death of some the people and so on. Such culture was not there at a basic level. Of course, the birth of a child of a emperor, that was recorded because that emperor would be very happy, and he says, okay, build a temple or maybe erect a structure in the name of my son or my daughter. Then only it will be there. For Aam Aadmi, for normal people like you and me, there wouldn't be any record. Okay, 100 years, 1,000 years back and so. Okay, or maybe 800 years back. In fact, I would be very surprised. I was very surprised that some people take pride in it. Okay, it's quite unfortunate. In fact, on the other day, I was talking to somebody. And then he said, oh, this particular saint is so great that nobody knows when he was born. I was like, sorry, we should be ashamed of that kind of system, that saint doesn't become so great if nobody knows when he's born. Okay, so that kind of ideology we had. Okay, if we don't know the birth record of somebody, we think that he's good, means he's great. Okay, that was a mindset we have even now. And you can imagine how would it be 800 years back or so. Okay. Well, yeah, the major breakthrough when it in the form of modeling, it came nearly after 100 years, 1208. Yeah, here onwards everything is AD, so I do not write AD again and again. So in 1208, this Leonardo Pisano. Okay. Maybe if I say Leonardo Pisano, many of you wouldn't recognize. If I use the word Fibonacci, you would recognize. Many of you would recognize. So in fact, the first model that he presented, it is some kind of entertainment problem. Okay. In the book of Liber Abaci. Okay. Liber Abaci. This is a kind of entertainment problem he gave. It's one of the first models. Of course, they are not realistic, but they give you some insight of how to start modeling. See, all these things you remember. This is 800 years back. Okay, before calculus was invented and before matrix theory was there. People hardly they were worrying more. Mathematicians were mostly worrying about solving algebraic equations and preoccupied with geometry. Okay, for them mostly mathematics means geometry and solving equations. At that time, this gentleman proposed the following model. suppose you have a pair of rabbits. Okay, a couple of rabbits, one generation. Maybe let's say that in the month of Jan. Okay, one pair of rabbits. Okay, they're born on 1st January. Okay, 1 month they mature, and then in Feb, what they do is they produce one set of offsprings. Okay, so in the month of February, you have this old offspring, old couple, okay, 1 month old couple, and their kids offspring. So in the month of March, what they do is they produce one more offspring. Okay, they are like brothers, the siblings of the earlier one, and then they die. So in this manner, what happens in the month of March? This one is an offspring of the first generation pair of rabbits, and then the second generation of rabbits will be there. Okay, and then after 1 month, since they are born on 1st February, let us say, after 1 month they mature and they produce one couple of, let's say, offsprings. And then in April, what happens? This couple again, they produce the newly born couple. They remain, and then they produce one more offspring, one more set of offsprings, and then it continues like this. So therefore, if you follow this principle, it is actually, it goes like this: Sn plus 1. At n plus 1th generation, the number of couples that you have is nothing but number of couples you have for the previous generation plus number of couples you have in the before generation. Okay, the generation before the previous generation. Okay, so this is the kind of equation you come up with. Okay, and of course since this is a two-step process, but Sn plus 1 is not just given in terms of Sn, it is given in terms of Sn and Sn minus 1. So what you need is S1 is 1, you just put S0 is 1. Okay, so this is the thing. In fact, this is a recurrence relation. Okay, it's a linear recurrence relation. I would like to ask BSc students, have you seen how to solve this linear recurrence relation? Is there any BSc student here? Have you seen how to solve this? No? Madam, is it there in curriculum in MSc or BSc? I know. How to solve the linear recurrence relations? In MSc, it is in the curriculum. Okay, fine. Yeah. So for BSc students, let me quickly give you a procedure. I will not do the details since it is there in MSc. So you assume that Sn is of the form something like a power n. Okay. I don't know what is a, and I'm just assuming that Sn is a power n. Okay? And you just substitute it here. A is an unknown here. So just substitute. You get a power n plus 1 is equal to a power n plus a power n. You cancel a power n minus 1 throughout. You would end up getting a square. What? A square minus a minus 1 equals 0. Now you have the value of a. It's a quadratic equation we can solve. What is a? A is 1 plus or minus root 5 by. Okay. Now you have two possibilities. Okay. 1 plus root 5 by 2 is 1 root, and 1 minus root 5 by 2 is also another root. So what you do is you write Sn is equal to C1 1 plus root 5 by 2 whole power n plus C2 1 minus root 5 by 2 whole power n. Okay. Here C1 and C2 are unknowns. Why did I write like this? Instead of simply writing a power n, why did I write C1, C2? Since it is a linear equation, okay, if you have a solution Sn and another solution Sn tilde, if you have two sequences which satisfy this property, then the linear combination also satisfies the same property. Okay, that's why you have this. So, of course, C1 and C2 have to be computed such that you have these two conditions set. Okay, you have these two conditions. Okay, compute C1 and C2. Yeah, and in fact, the most important feature here, which fascinated people at that time, was not this solution. What fascinated was, if you look at these numbers, what are they? 1, and then it is 2, and it is 3 in the March, and then next is 5. Next one, how do you compute? You have to add the previous 2, 8, 30, 21, and so on. So this is called Fibonacci sequence. Okay, Fibonacci sequence. And what fascinated people was the ratio of two consecutive terms, okay, in the limiting case. Limit n tends to infinity. So what is it? In fact, it turns out to be, since we solved it completely, now we know what is the limit. The limit is actually 1 plus root 5 by 2. Okay. In fact, this is called golden ratio. In fact, this is it has a lot of geometric applications. This golden ratio, you can read it in this Mac Tutor or other websites about this golden ratio. There are plenty of literature available. In fact, this golden ratio is attributed to beauty. Okay. In fact, before this Fibonacci thought about this Fibonacci sequence and golden ratio itself, thousands of years before it, there were structures in ancient Greek civilization and Roman civilization whose geometry has this beautiful structures whose geometry incorporates this golden ratio. Yeah, and in fact there was a research, and there was a survey on what many people thought was beautiful face. Okay, and the surveyors, they actually found out that suppose you take a picture of a person, male or female, it doesn't matter. You just draw, put it in a rectangle or something. Okay, you look at the ratio between this length and breadth. Okay, and in fact this has to be a golden ratio. Of course, there's exactly some places where you have to measurement there from which you have to start your taking measurements and so on. Yeah. Anyhow, so when I learned from Professor C.R. Rao, Doyen of Statistics, supposed to be the best statistician who is living on this earth today. He's 1 or 2 years old or something. In fact, he explicitly mentioned some names which I don't want to mention now, that they are highly acclaimed to be very beautiful. And when those measurements are taken, in fact, it's exactly matching with this golden ratio. Okay? Measurements of faces, different parts of the faces. Yeah. Anyhow, so this is about this golden ratio and so on. Let's come back to this population thing. This is all discrete level. This 0.08 and so on. That is discrete. So next major breakthrough came in 1798 by Thomas Malthus. Okay. So this is the first to create mathematical model for population growth. Okay, he's a Britisher. In fact, he's a cynical Britisher. He has written an essay on population dynamics. It is some 80-page long essay. Many times I tried to read it completely, but after reading more than 1 hour, I fell asleep because it doesn't have any mathematical equations. Okay, it's just like a philosophical book. Yeah. So in this book, what he proposes is this particular philosopher, the rate of change of population. Suppose P of t represents population at time t. Okay, and suppose B is the birth rate. Okay, per capita birth rate, and mu is the mortality rate, per capita mortality rate. Okay, per capita mortality rate means what? If you want to compute total offsprings that you are going to get, okay, so you have to use B into P. Okay, and then this M into P is the total number of people who are deceased. Okay, so B of P minus M of P is actually that this describes the change. Okay, so this is d by dt of P of t. Okay, this is a very fairly simple model. Okay, so you just call B minus M. Oh, sorry, I'm using mu for mortality. Okay, mu for mortality. It is something like B minus mu P of t. Okay, it is P dash of t. So this is a ODE. I'm sure all of you can solve it. Okay, you can solve it using separation of variables method. Okay, dp by dt is equal to this. You write it as dp by P of t minus okay, what is it? Minus B minus mu dt. Okay, is equal to constant. This is a solution. Okay, of course, you evaluate constant by substituting the boundary substituting the initial condition P of 0 is equal to P naught. And if you do that, you end up getting P of 0 e power B minus mu into t. Okay, so this is what I would get. In fact, this B minus mu, some people call it as R. R stands for intrinsic growth parameter. It's a small r. Okay, intrinsic growth. Or some people call it simply call it as Malthusian parameter. Okay, Malthusian parameter. Yeah. In fact, nowadays in the media you would see R naught. Okay, when they discuss about COVID modeling, they talk about R naught. Actually, this is a kind of primitive version of R naught. Okay, small r. R naught basic reproduction number. If time permits, I'll talk at the end of the day, end of the lecture. Right. So P of t is like this. So what is it? It is actually e power RT. So if R is bigger than 0, then what happens? If R is bigger than 0, as t goes to infinity, what happens? R is positive. As t goes to infinity, this goes to P of t goes to where? It goes to infinity. Okay. If R is negative, this is when R is positive. If R is negative, what happens? So what is e power minus 2t? What happens as t goes to infinity? Goes to 0, right? Similarly, bar is negative. This goes to 0 as t goes to infinity. Okay. So Malthusian model, it predicts only two things. It says either population goes extinct. This is a situation. This is extinction. And second one is, this is extinction. Extinction of population. And the other one is blow up of population. But you would see that in reality, you don't see any population which is blowing up. Okay, there are very, very few things which are getting extinct. Okay, you see ants or cockroaches, you never see blow up. Okay, they, of course, they increase, but increase only up to certain level. After that, they are bound to decrease. So this is what is the model by Verrill, and he's a French guy. It is in 1838, nearly after 40 years. So Verrill. So what he says is, you have this Malthusian parameter R, which talks about intrinsic growth, but at the same time, population cannot go to infinity or cannot come to 0. There is he introduced a notion called carrying capacity. Carrying capacity. Carrying capacity means it is a maximum population that are sustainable in given conditions. That is called carrying capacity. So what he says is nature decides carrying capacity. Nature means surroundings, okay, availability of resources and various other things. They decide carrying capacity. Once K is there, then population cannot grow beyond K. That is a theory of Verrill. Suppose forcefully you bring more and more population and keep it in a place which is more than this population that you are artificially putting in a place is more than the carrying capacity of that place. Then what happens? Population dies. Nature feels this extra population. Okay. And then eventually you tend to this K. And what is this? Why carrying capacity is important? That's more practical because you don't have infinite food. Okay, you have a limited food. You don't have infinite place to stay. You have a limited place to stay, right? Human beings, suppose if their population is instead of 700 billion, suppose it becomes these many crores, let us say. Human beings cannot survive. Okay, they're bound to die, and in fact, they're bound to die soon because there won't be these many crores. There won't be enough space for these many crores of people. There won't be enough food for these many crores of people. So people die of starvation. People die of various disease and so on. Because not all people can be given medical facilities and so on. Okay. So because of limited resources, this carrying capacity is introduced by Verrill in 1838. Yeah. So what is that model? It is actually adding some extra term to Malthusian model. Malthusian models talks about d by dt of p of t is equal to r into p of t. This is what Malthus said. And now what Verrill is saying is, if you just put 1, it is Malthus, and he says p of t by k. Okay, so this is what he says. Of course, It is again a ODE, first order ODE, which can be solved using separation of variables. And of course, what you have, since it's a second order polynomial, second degree polynomial, factors are also there for P. You can simply do partial fractions and solve them explicitly, and you can write P in terms of T. Okay? Maybe I'll write a little later. Let me tell you about Verrill a little more. So in fact, he made a lot of experiments, okay, and he said carrying capacity K for the Belgium. Belgium is a country which has border with France. Okay, it's next to France. So carrying capacity for Belgium. Okay, so he says it is 9.4 million. That's what he says. In fact, I will tell you that the population of Hyderabad is more than 9.4 million today. Okay, and he said Belgium is a country. No, it's not just a city; it's a country. He says for Belgium, carrying capacity is 9.4. That means you cannot have population more than 9.4 given the conditions in Belgium. So this is something that he has predicted in 1938. Okay, because at that time, Belgium population at time t equal to 1838, it is equal to 4.3. Okay, so nearly 200 years back, 4.3 million. So he said 9.4 is something that it can be sustained. And in fact, if you see Belgium population in 2017, it is something like 10 million, approximately. No, sorry. What is it called? 2017, its population is, I think, something like 11.3 million. See how accurate it is. He predicted for 200 years that it cannot be more than 9.4 using his experiments. And after 180 years, the difference, the error of his prediction, after nearly 180 years, it is around, what is the difference? What is the difference? Just find out. Okay, so accurate. Of course, many people who support this Verrill model, he says this difference is due to immigration and the various world wars and various other things. But anyhow, see, I tell you that in mathematical modeling, no model is perfect. Okay, in every model, you make some assumptions, you make some compromise. If there is no compromise, then model will be extremely difficult, and the mathematical tools that you have to analyze the model will be useless. So that's why what mathematicians do is, first they give you a simpler model. Okay, they analyze it completely using the mathematical tools, and then from the information that you have after analyzing the model, you will improve the model. Okay, by adding some more term. Okay, this is what happened in the case of Thomas, Malthus, and Verrill. First, after solving this Malthusian model, after solving this equation, then this repair has been done. Okay, and then after that, okay, and then you improvise it, and then analyze it, improvise it, and so on. This is everlasting process. So that's why no model is perfect. Okay, always there is a scope for improvement in view of latest developments in mathematics. Okay. Whatever heat equations and wave equations that you have studied, in fact, at the time of Fourier and at the time of Euler and so on, they were D'Alembert and so on. They were doing fine, but with modern mathematics and with modern measuring instruments, there is a lot of scope for and need for new mathematical models, even in the context of heat equation and wave equation. That's why there are nonlinear models when it comes to wave equation and heat equation. In fact, I'm talking this for PDEs. Then imagine how much scope will be there for improvement of ODE models. Anyhow, so if you solve this equation using partial fractions, you end up getting this P of t is equal to k e power rt by e power rt minus 1 plus k by p. Okay, p naught means p of 0 is p naught. So for t very, very small, what happens? If t is very small, then e power rt is very close to 1. This doesn't work. This becomes 0 when t equal to 0. T is very close to 0. This k and this k, they get cancelled. If t is very close to 0, then p of t is very close to the earlier thing, p naught e power rt. Okay, it behaves as if it is a Malthusian model. Okay, and then that means it increases exponentially, but there is a barrier. Okay, k is the barrier, carrying capacity. You are saying that you cannot cross k. That means population cannot grow beyond k. Okay, it increases exponentially to begin with, and then after certain stage it becomes flat. Okay, because if p of t is very, very close to k, then what happens? If p is very close to k, then what about 1 minus p by k? 1 minus p by k, if p is very close to k, that is very close to 0. Okay, that means d by dt of p is equal to r into p of t into something which is very close to 0. That implies this p dash of t is very close to 0. That means it is like flat. Okay, it doesn't increase much. Okay, in fact, this is a heuristic way of explaining how things work. Of course, one can do it very, very rigorously. Okay, in fact, in my book on PD on ODE, I have explained how to solve this autonomous, how to find the long-term behavior of this autonomous equation without solving them explicitly. Okay, without using partial fractions or anything, you can actually analyze the long-term behavior. P of t goes to where as t goes to infinity. This you can find out without actually solving the OT. Anyhow, so initially, if p naught is bigger than k, it reduces to k. Okay, so this is what is the carrying capacity. This is what is the role of carrying capacity. Yeah. And the next one is by this major breakthrough, I would say, and the beginning of modern population dynamics. This is in the 20th century, early 20th century, by Lotka, okay, and his collaborators. And he has written this, Lotka in 1907 has written a seminal paper. It's only a 2-page paper. 2-page paper. It's very surprising to know the impact of such a small 2-page paper. Okay, and 1911, same guy, Lotka. Of course, Lotka with Sharpe. Okay, so in these two papers, they introduce what is called renewal equation. And of course, again in 1922, this Lotka. This is in Proceedings of National Academy of Sciences, USA. This is one of the prestigious journals in science, including mathematics. Okay, PNAS USA is highly prestigious. Of course, we have PNAS, Proceedings of National Academy of Sciences. India is also there, but it is not as famous as USA. It's mostly due to Indians, I would say, because I tell you, as a researcher, if we have a fantastic paper, fantastic results in mathematics, we try to send it to a US journal, okay, like Annals of Mathematics and so on, okay, or Inventiones, or PNAS, and so on. Mostly US based journals dominate the scientific community in India and in the world because of their reachability, okay. If you publish a paper in local journals, okay, to bring up the standard of those journals, then journal quality may improve over the period of 20-25 years, but the guy who publishes in that, he will not be popular. Okay, so that's why this capitalistic way of doing of science, this is dominating nowadays. In fact, Russians till the end of Cold War, till 1980s, their best work they are publishing in Russian journals. Okay, so they never cared about recognition in the Western world. In fact, so many great works of Russian mathematicians, they were translated later after Cold War to English and issues after issues were published by American journals. I wish we are also rich enough to do such kind of things. Yeah. Anyhow, so what are the speciality of these models? They introduced what is called structure in the population. Okay. So what is structure in the population? So far, when I say population, I'm writing P of t, population at time t. If only population at time t and nothing else, you don't know how many kids are there, you don't know how many women are there, how many men are there, how many old people are there, then there's very little that you can do with there's very little that you can decide about that total group population. It is impossible to make any policy. For example, if you want to make healthcare policy, okay, suppose you want to make education policy, or maybe military policy, you should know how many people are there at various ages. Okay, suppose there are plenty of people between the age 0 to, let's say, 12. A lot of people are there. Then the governments, when in their policy making, then they should say that, okay, these people will come to colleges, okay, in next, let's say, 5 to 10 years, many of them. Then what you need to do is you have to build a lot of higher education institutes, okay, a lot of colleges. Okay, suppose there are more people are there in the age group 70 to 80, like Japan. Then their focus should be on healthcare system, okay, compared to the education. So once you know how your population is distributed, okay, then you will know you can actually make decisions regarding policies. So that's why it is very important to know population as a function of x as well as t. Okay, here x is age, t is time. Now p of xt denote the population density, okay, at time t having age x, okay, density of the population. Okay. In fact, these Lotka models I'm not going to write, because Lotka models are in some sense they are given by renewal equations, which can be obtained from the model that I'm going to describe in a minute. Okay, so these are basically integral equations. Okay, they're basically integral equations. Now I will write a differential equation and I'll tell you how to write integral equation from the differential equation that I'm going to state, that I'm going to write. Yeah. Right. So the work that I'm going to describe now, the equation that I'm going to write now, it is due to a physician. It's a medical doctor, you see. He's called McKendrick. He was working in India, and at the time he's a British physician. Okay, British physician. At the time, plague was rampant in India. Okay, many people were dying because of so many infectious diseases. So he had a lot of data coming from India. He was working in India, yeah. And then he gave a formulated model for epidemiology. That means spread of infectious diseases. Okay, 1926. This is a very important paper, population dynamics, by McKendrick. And in 1959, exactly same model was rediscovered by somebody, von Foster. Okay, when he was studying the growth of cells. Okay, actually, this McKendrick was studying, dynamics of human population. Okay, and von Foster was studying cell growth. And the underlying principle was same. They came up with the same model. Okay, let me tell you what it is. As usual, let P of xt denotes the population density, and let mu denote the mortality rate. Now, mortality rate is a function of x now, because earlier mu was constant in the case of Malthus model, because you cannot write mortality depends on time. That's nonsense. That means that if it is 2022, many people die. In 23, less people die. It is like almanac. Okay, which has no scientific, which is non-scientific. This mortality rate, it will depend on x, the age. Okay, if the age is more, then more people, then the probability of dying is very high. Okay. Similarly, this B, the birth rate, that is also the function of x. Okay, because initially at x very small, the individuals will not give birth to offsprings. Only after certain stage they start producing offsprings, and only after certain stage, okay, after that they don't produce offsprings. That is a basic thing. But for theoretical purpose, you can imagine that there is no such rule. One individuals from all possible ages produce offsprings at the age of B with the rate B of x. So typical B of x graph will be like this. Okay, so this is 0. This A dagger is maximum age. This is B of x. Okay, yeah. So of course there are other types of shapes also possible, but I'm telling you, this is a most natural thing to assume for mathematical model. Yeah. So with this thing, the change, this P of x, so this is actually partial derivative plus dt dt. Okay. So this actually denotes the directional derivative of P in the direction of 1, 1. Why one has to take it? You will come to know once I complete the model. Okay. Plus mu of x into P of xt equal to 0, and the newborn offsprings, that means when x equal to 0 at time t. So newborn offsprings at time t, they come from already existing individuals, right? These newborn babies, they should come from existing individuals. Existing individuals at time t. Okay. So newborn babies in 2022, they will be from those who are alive in 2022. Right? This is means from all possible individuals from P of xt. Of course, with this B is the birth rate, B of x, and this it is you have to integrate because it comes from all possible individuals. So this is what is the boundary condition. Of course, initial data you can take it to be like, let's say P of x0 is equal to P naught of x. Okay, so this is what you have. And then suppose mu is 0 for the argument's sake. Mu is identically 0, B is identically 0. What does it mean? There is no mortality, there is no fertility. Nobody dies and nobody is born. Then what happens? In that case, what happens to the model? It is Px plus Pt is equal to 0. P of x0 is equal to P naught of x. So one can easily check that P of x comma t is equal to P naught of x minus t. It is a solution. In other words, P of x comma x plus h, T of x plus h is equal to P of xt. Okay. So what is it? It actually says, suppose there are in 2022 there are 100 people in a village having age 5. Let us say. Okay, there are 100 people in 2022 in a village up to age 5. Then suppose there is no mortality and there is no fertility. Then what is the situation of this 2122? Exactly after 100 years, what is the people? What are the number of people with age 105 years old? It is exactly 100 because they neither increase nor decrease. It's the same thing. This is what is given by P of x plus h. In this case, x is x is 5, t is 2022, and h is 100. Okay, and it happens for every h positive. Okay, so this is why in fact, once you have this, when there is you have this in the absence of mortality and fertility, this is nothing but px plus pt. Okay, this is nothing but px plus pt. That's why I wrote px plus pt. It is by characteristic method. Okay, once you know basic PD, then you can easily do it. Okay, so this is the McKendrick first model. It talks about, it is a linear equation. The main difficulty here is due to the non-local term. Okay, you need special tools to address this non-local term. In order to compute solution at t at some t, this is x-axis, this is t-axis. You want to compute solution at this stage, then you need to have an understanding of the solution pxt, where x is running from 0 to a dagger. That means you should know solution on this entire straight line. Then only you can compute solution at this point. Okay, this is a major difficulty. Okay, such kind of problems are called non-local problems, and in fact, there's a lot of work going on non-local problems. In fact, it's a very difficult part of PDEs. Okay, these non-local problems. Yeah, and in 1974, another breakthrough in this direction is, see, so far this mortality and fertility, they are taken as functions of age. They're saying that, okay, mortality just depends on age and nothing else. And fertility also depends only on age and nothing else. But in reality, that's not the case. Okay, it depends on other environmental factors also. And it depends on how well one can compete, how well an individual can compete to get food, okay, and to get a partner and various other things. So therefore, what he says is mu, it is not just a function of x, it is a function of another function where S of t is actually total population. Okay, it is equal to, this is the main contribution due to Guttin. And in fact, the Guttin and McCammey's paper is a very seminal paper. Okay, 1974 Archives of Rational Mechanics. Okay, and of course later on people introduced why should we take total population? Why not psi of x, weighted population? Why the weighted population? It is because individuals of different ages will have different contributions when it comes to competition. Okay, suppose there is a war and you have mostly oldies in your country, then you can't fight war. Okay, you can't simply take my population, total population is very high, integral p of xt dx is very high, so I can go for war. No, you should not go. Okay, so you should see how many people are there with different ages. This psi is the one which helps you in understanding that. Okay, yeah, and in fact these kind of models can be extended not only in population dynamics of cells and humans and cancer modeling, because there also it's a cell growth, cell growth and so on. One can use it in other interesting contexts like currency modeling. I'm going to stop in next 3 minutes. Okay, same thing can be used in currency modeling. In fact, what people, this Rausch and Quirtioli, okay, they have written an interesting paper on currency modeling. Because see, we got to know this at the time of this Notebandi, 2017 or so. No, this gentleman from our Prime Minister came to television and announced some very shocking thing, and we are all standing in long queues. And then at that time, we were interested in what are the models in currency hoarding and what is a hoarding pattern. Okay, in general, not just in India, in general, what is the work models in this? So in fact, we found out an interesting paper written by these people whose model looks similar to this McKendrick one first model. So suppose C denotes the currency in circulation and H denotes currency in hoarding. Okay, and then this CT plus CX. Like earlier thing, these currency notes also, they have this mortality rate. That means these notes, they will be soiled, that old notes, the wear and tear issues will be there. Okay, if you go to a shop and a guy gives a half-torn note, you say, oh, give me a different note. That's what you would say. So that means these things, these soiled notes, they should be taken out of the circulation. Okay, once you go to the bank and give it to them, so they just burn it, or they do whatever they want. That will not be that will not be in the circulation. It will be out of the circulation. So what I do is, it's like mu C. Mu is the mortality rate, which depends upon the age of the note, age of the currency note, into C. This is equal to, you see, let A be the rate at which people hoarding phenomenon. So therefore, you have to put minus AC here, A C of xt. A is a constant. A is the rate at which currency goes for hoarding. Okay, maybe people keep it in locker, or I don't know. There are so many ways of hoarding this. That is something that which goes to black money. Okay, it's not unaccounted for. And whatever it goes from currency, whatever it goes from circulation, it will come to hoarding. So H denotes currency which is in hoarding. Is you have minus AC, it will be plus AC. Okay, and see, if somebody hoards it, then he will not hoard it indefinitely. No, at some point of time he has to take out whatever money he is hoarding or she is hoarding. So let us assume that it comes out with the rate B. So therefore you have to take it, subtract it from here, and then add it from here. BH of xt. And of course, this CFT0, okay, this is like D1C, 0 to infinity, or something, whatever maximum age for this currency in circulation. It depends on various bills. 100 rupee note will have a different, mortality rate, and 50 rupees bill will have different mortality rate. Okay, because they use different quality paper and so on, different sizes. Yeah. So this is a kind of model that we had. And what if the government withdraws money for some reason from circulation? Okay, and what if government pumps money? So, and what are the dynamics of C and H for T sufficiently large? Okay, so whether it comes to a steady state, or what happens as for large T? That is a question. Okay, as T goes to infinity. This is an interesting model. Okay, in fact, myself and Professor Vasudev Murthy, we worked on this model in 2018. Okay, we got, in fact, very, very interesting results. Okay, so what I want to say is these models, though they originate from population dynamics, cell dynamics and cell growth and so on. Once you understand the mathematics behind it, then you can apply to other branches of science also. Like we could apply it for economics. Okay. And in fact, same time in 2017 and so on, this kind of tools, when we have diffusion, we have applied to models which come in neuronal networks. Okay, so the message is, once you are good in mathematics, okay, once you understand these PDEs, then you can very easily work in interdisciplinary subjects. Okay, and there is no what is it, boundary that okay, I'm a mathematician and I don't look into physics things, I don't look into biology things. No, it's nowadays the barriers between subjects, they are no longer there. Okay, 2000 years back there were no barriers between various branches of sciences. Okay. That's why your PhD, it is not like it, the degree doesn't say anything about subject. Okay, philosophy, doctorate or something. Okay, and philosopher, these scientists, they used to be called natural philosophers or something. Okay, if you look at Aristotle, Archimedes, and so on, basically at that time he was known as philosopher. Okay. So at that time, there were no barriers between sciences. Since science has grown up too big, grown up beyond imagination. That's why, you know, a lot of barriers are there, and it's very difficult for a person to work in more than 1 or 2 areas in their choice, in their choice of subject. But nowadays it is again going to the backwards. Now more and more of interdisciplinary research is going on, and I want my youngsters who are attending this to keep this in mind, and don't have aversion for biology if you are a math student, and biology students or medical doctors, so they should not have aversion for mathematics and so on, because there's a lot of scope that we can work together. Okay, so with this note, I thank I thank you for attending my lecture with patience, and if you have any questions, I will be happy to answer. Yeah. No questions? So if there are no questions in this talk, you can ask any other question. Okay. So, in mathematics.
Participants, if you want to ask any questions, you can ask. Otherwise, you can put in the chat box.
Yeah.
Thank you, sir, for readily accepting our invite in spite of your busy schedule, and for enlightening us by your lecture, sir. Now I call upon Harita to propose formal vote of thanks. Sir, a small appreciation certificate for you, sir.
Thank you. Thank you very much.
Welcome, sir.
Madam, am I audible?
Yes, you are audible.
Good afternoon to one and all. I be Harita, Assistant Professor, Department of Mathematics and Statistics. It gives me immense pleasure to propose vote of thanks for this session on differential equations in population dynamics. At the outset, I thank our resource person, Dr. P. Sumant Kumar, sir, Associate Professor, School of Mathematics and Statistics, University of Hyderabad, for his excellent and fulfilling presentation on this topic. Sir, you enlightened all of us with your talk by quoting various examples from the articles like Fibonacci golden ratio, Verhan theory, Lotka theory, Kendrick, von Foerster's non-local problem, currency modeling, and how the population dynamics were there during the Bevel years. I hope all the participants gain good knowledge today with your lecture. So once again, I thank you for accepting our invitation in spite of your busy schedule. I sincerely thank Professor K. Mitcham Reddy, sir, Honorary Secretary, Hyderabad Mahila Vidya Sangam, and Professor G. Sudarshan Reddy, sir, Secretary cum Correspondent, RDVR Women's College, and extend my heartfelt thanks to our beloved Principal Dr. G. Achita Devi Man and Vice Principal Dr. Kavita Man, and Coordinator of this program, Shweta Srivatsava, Head Department of Mathematics, and all the members of the department for their cooperation. And also, my heartfelt thanks to all the participants for their patient listening. Thank you, ma'am, for giving me this opportunity.
Okay, thank you very much. Shall I leave?
Thank you, sir.
Yeah, I'm leaving.
Thank you, everyone. And we will be joining for the next session tomorrow at 11 o'clock. All of you note this, as there is a change here. At 11 o'clock tomorrow morning, we'll have a session by Professor Nikita Agarwal, madam. Thank you, everyone.
Thank you, ma'am.